Okay, chapter 3, methods of calculus, section 3.1, improper integrals. So you know from year 12, if you want to calculate the area under the curve, a curve, you're going to use calculus method of integrating between the limits a and b, the function, let's say f of x with respect to x. Okay, so if this is y equals f of x. Now, this is a proper integral if both the function is continuous and defined on the interval between a and b. Okay, interval, it's a closed interval, so all the x's are between a and b. Okay, improper integrals are very similar to this, but this time we have got some difficulty in continuity of the function, or function might not be defined at one or both limits, or anywhere else in between the limits within the interval. So here's the definition. So it's one or both limits are infinite. So over here there is an asymptote. So I don't know if this is y equals 1 over x minus 1 function. Clearly for x equals 1 this will not be defined. So but if I said work out the this area, so the integral between 1 and 3 of 1 over x minus 1 dx, so you could see that this one here is undefined. So this actually is going to be undefined over here because it's a limited value. If you want to if you have an example of limit being infinite, you could actually open it all the way to the end. So let's say this side, and let's say you want to find between 3 and infinity. There you go. So then clearly what do you do with this infinity in this example? If you wanted to talk about the function is not continuous, so it's undefined at one point in the interval. What if you consider an interval between, let's say, 3 and minus 3? So you're talking about all of that, okay? And then you want to be you'll be attempting to find the integral between minus 3 and 3, and clearly this would be an improper integral because when x is equal to 1 this function is undefined. So we are going to consider all those cases. In some cases we'll be able to find a value of that integral, so the area, it will be possible to actually evaluate it. And then we'll call that situation a convergent integral. In other cases you will not be able to find it, it will be impossible, then it will be divergent. Okay, so I'll show you how to do it on an example, which is let me just have a look. Okay, before we do example from the textbook, let's have a go at the function. Let's say okay, there you go. So let's consider the function y equals e to the power of minus x dx. So it's your e to the power of x reflected in the y-axis. So this is y equals e to the power of minus x, and we're going to find, let's say, this integral. So it's between 0 and infinity, e to the power minus x dx. So how are we going to proceed? So what we're going to do, we are going to actually replace infinity with t, and we are going to try and find the limit as that t tends to infinity. So the way you can write it, it's limiting value of t tending to infinity of the integral, and this time we replaced it with t, the infinity, the top limit, dx. And we'll keep on writing the limiting value all the way through, and it's going to be, it should really be positive infinity, but over here we're going to find the integral. E to the power minus x is going to be minus e to the power minus x, so you integrate as you normally would do, then you're going to put the limits in as you would normally do, but the answer you're going to get will be in terms of t until the end. So we put t in, you're going to get minus e to the power minus t, and then minus, if you put 0 here, minus e to the power of minus 0, so 0. So that gives me a limiting value of t tending to infinity, minus e to the power minus t plus 1. Okay, and now you just need to evaluate it. So minus e to the power of minus t is minus 1 over e to the power of t. So what happens to this as t tends to infinity? The denominator gets really, really large, so 1 over the denominator, that will tend to 0. So that will go to 0, you will be left with 1. There you go. Okay, so this actually a little area that tends, it would take you infinite time to reach to the end. You'll never reach there, but it actually has got the limiting value of 1, which means it gets closer and closer to 1. Will never get bigger than that. Okay, so we'll go through an example, the example 1 in the textbook. So here we are asked to, I've just copied the question. I think we need to evaluate it. If it exists or if it doesn't exist, it might be convergence like this one because it existed, or might be divergence. So over here, if you had the power of positive t, it would diverge, it would not be defined. Okay, so over here we just simply first of all deal with the limit. We're going to use the substitution. T is infinity, and we're going to find what happens when you are considering limit of t tending to infinity of the integral between the limits of 1 and t. It's x to the power minus 2 dx. Okay, so this is going to be, let's just evaluate it. Well, find out what it is. It's add 1 to the power, divide by that power. It's going to be minus x to the power minus 1 between 1 and t. Let's substitute. You have to keep on writing that lim at the start till you start evaluating it. So this is going to be minus t to the power of minus 1, and then minus 1 to the power of minus 1. Let me just write it sort of in a more user-friendly way. So this will go into minus 1 over t, and this will just go to minus 1. So it should be minus 1, by the way. So that will go to plus 1. Okay, let's sub t in there. So this is exactly, well, similar to the example I did before. This will go to infinity, so 1 over t tends to 0. So you've got 0 plus 1. So you're going to get 1. So it converges. Okay, over here, first of all, you've got 1 over x. It's not defined for 0, but we're not there, but it also, we've got the infinity, we need to be replaced with t. So it's t tends to infinity. We're going to consider this integral. So it's going to be ln. We're considering positive values only, so you don't need to put ln of modulus of x between 1 and infinity. So we're going to 1 and t. I'm going to write it as ln t minus ln 1. ln 1, that's equal to 0, so we've got just ln t. If you substitute instead of t infinity, you know, ln infinity tends to infinity, although very gradually. It will clearly diverge. Okay, so undefined because that tends to infinity. Okay, so this is example 1. We're going to look at example 2. We're going to find the following integrals, and if they exist, obviously if they don't exist, you need to state that it diverges or doesn't converge. Okay, so let's just draw it quickly so you know what it looks like. So this is your 1 over x, so we're talking about this area between 0 and it's undefined at 0 and 1. So this is the problem here. So we're going to let t is equal to 0, and we're going to find the limiting value as t tends to 0 of that integral. Your t needs to be 0 needs to be replaced with t. So we're going to add 1 to the power and then divide by that power. So you're going to get minus x to the power of minus 1. So you're going to get, let's sub the limits in, minus 1 to the power of minus 1 is going to be minus 1, minus t to the power of minus 1. So you've got minus 1 plus 1 over t. Let's just write it in that nicer way. Minus 1 plus 1 over t. Okay, so what happens here if I put something really close to 0 in the bottom of the fraction? So I know 0.0001, for example. When you flip it, that will be 1000. So if you flip a tiny almost number that's almost 0, you are going to get infinity. So this one clearly tends to infinity. So you're going to have divergent answer, or does not converge. So is not okay. Let's look at part B. Okay, so first of all, let's establish, if you look at the denominator, you've got 4 minus x squared. If you've got a fraction, you should know that if you make the denominator equal to 0, it will give you an impossible calculation to do. So that will give you an asymptote, or it's not going to be defined at that particular value. So that happens for x equals plus or minus 2. So here clearly we've got 2, so our t is going to be equal to 2. So we are going to have a look what happens when t gets closer and closer to that 2. How does that function behave? Okay, so let's have a little let's just calculate that integral. I'll do it on the side here. It just doesn't have to have a limit. Let's just find out what it is. Okay, I suggest doing it by substitution. So remember, I normally ask you to replace the denominator, or the one with the weird power, if you were to bring it to the top, with use the substitution for that. So I'm going to substitute that. So substitution. Then you're going to find du dx, which is minus 2x. So du is equal to over is minus 2x dx. Let's just stop there. Imagine splitting the x onto that side. Okay, so we've got x dx present over here. I can replace it with du over minus 2. So let's have a go at doing that. X dx is minus a half du. Okay, so let's do this substituting. So x dx is minus a half du, and in the denominator you've got u, square root of u. So let's just integrate it. So it's minus a half u to the power of minus a half du that we need to integrate. So add 1 to the power, divide by that power, you're going to get 2 u to the power of minus a half, which is minus u to the power of minus a half, which is minus 4 minus x squared to the power of minus a half. There you go. Okay, so let's minus a half. I was just thinking that doesn't make sense. If you add 1 to the power, you get plus a half. Okay. Right, so let's now do the next step over here. I know what this integrates to this, so that is going to be equal to limiting value as t tends to 2 of minus square root of 4 minus x squared and 0 and t. Let's substitute the top limit in. That will give me 4 minus t squared minus, substitute 0 in, so it's minus square root of 4 minus 0 squared. That will give me minus 4, sorry, minus square root of 4. So that will get plus 2. Okay, so now what happens when you put t equals to 2? That will go into 4 minus 2 squared and then plus 2. So altogether this will go to 0 plus 2, so it's going to be 2. So at this moment we're just substituting 2 into that, so it converges. Great, so let's have a look at another example. This time we're going to consider a situation where both limits are undefined and we need to replace both of them. So in this case, if both of the limits are infinity, so in we're not going to sketch it, but give you an example of probably very similar to this. It could look like this, okay, and then you've got that could turn infinity, minus infinity to plus infinity. You want to see what is the area under the curve. So in this instance, what we're going to do, we are going to just choose random number between minus infinity and infinity. So in this case, I know probably would be a good idea to choose 0, but if you want to be awkward, choose a different number. That's perfectly fine. And consider 2 separate intervals and then combine the answer. But out of those 2 separate intervals, if one of them is not convergent, then obviously that won't work at all. Okay, so first of all, let's just have a quick go at integrating this function. You may actually look at it and know exactly what the answer is going to be, but you could do this one by substitution, or you could, yeah, by substitution is the best. So we're going to replace the power. Let's just do it in red so you know it. So the awkward part is that power, so we're going to use the substitution for that. You need to differentiate that chosen substitution, and then at this point I normally rearrange it by splitting du and dx, and just pause for a second to see if I've got something like this going on here, and I do. I've got x dx, so x dx can be replaced with minus half du, and I'm ready to carry out my substituting. Okay, so our integral is going to be, no, x dx is going to be minus a half du. E to the power of minus x squared will become e to the power of u. So we just need to integrate e to the power of u, which goes to e to the power of u. And that is minus a half e to the power of minus x squared. Obviously that should be plus c because it's a part of a question. If in exam potentially you could lose a mark. Right, let's have a go at doing this. So we're going to split it into 2 integrals. Okay, we're going to consider it as minus infinity. Let's stop at 0, and xe minus x squared dx, and then from 0 to plus infinity. There you go. So I'm going to do those 2 separate ones. Let's call this one I1 and that's I2, and I'm going to come back to this page afterwards. Okay, let's get a new piece of paper. Okay, so in this particular case, let's have a look at I1. So it's the one over here. So I1 is the integral between minus infinity and 0 of x e to the power of minus x squared dx. Right, so obviously it's defined for 0, but it's not defined for minus infinity. So that at this particular point we're going to replace that minus infinity with t. So let t is equal to minus infinity. And we're going to, once you start replacing infinity with t, we're going to consider t tending to minus infinity, and the integral becomes t to 0 x e to the power of minus x squared dx. We have already evaluated that, well, found the answer to this integral. It was minus, let me just copy this down first, minus a half e to the power of minus x squared between t and 0. Substituting the limits is the next step. So this one will go to minus a half and then e to the power of 0 minus a half e to the power of minus t squared. So e to the power of 0 is 1. So you are going to get minus a half times 1, so minus a half plus a half. Now let me pop this into the denominator just so you could see that when you substitute minus infinity squared will become plus infinity. So 2e to the power of t squared, that tends to plus infinity, a really large number. So if you do 1 over 2e to the power of t squared, that will tend to 0. So the answer is minus a half. So it converges. This I1 exists. So let's have a look at I2. I2 from 0 to plus infinity. So over here we are going to have limiting value of t tends to minus infinity. This time we've got 0 and infinity of minus, let's just write it straight away, as the limit. I understand it's not on that side normally written, but it doesn't matter. I've done that one like this. So we're going to, oh sorry, that should be t by the way. Messed it up trying to save on space and then end up being a little bit of a mess. Okay. Okay, so let's, that should be plus infinity as well. Just double check, this was rushing it. Okay, so we are going to plus infinity and we've replaced the top. Yeah, perfect. Okay, so it's t tends to infinity. What happens here? We are going to have minus a half e to the power of minus t squared minus a half e to the power of 0, because that's the lower limit. So that will go to plus a half and that will go to minus a half. Let's write it in the denominator the same way as before. So over here, very similar expression to the one before, that clearly tends to 0, and then you are left with a half. So again, it exists. So we've got two limits, two values exist, and oh, there you go, let's come back to the point before. So we've got the answer to the first one is minus a half, and the second one is a half. So altogether it's 0. Perfect. Okay. It looks like it actually might be one like that. Yeah, it makes sense because it goes through 0. So you have got, that will be the same area but negative, and that actually will be on the other side because from, no, that's right, that would be negative, that's positive. So anyway, have a go in GeoGebra or graphical calculator and sketch it for yourself to check. Okay, let's have a look at section 3. That would lead us to exercise 3a. Okay, and then we'll go on to section 3.2, and this is a completely separate section, a new idea coming up next.